Hello, this is Mr. Gilmore with the 4.5 Part 2 Parallel Application Proofs. Now that we have these theorems in place, these parallel tests and parallel consequences, let's take a look at how they unfold in several other theorems that we'll take a look at. One is, in fact, a good question, which is parallelism transitive? And the other will be taking a look at a claim of Euclid. We'll finish off the lesson with actually several just application problems using our consequences and our tests. So transitivity. We know transitivity works in many different relations. We've seen it work with transitivity equality. We've seen it with the relation of congruence. We'll even see it with the relation of greater than. But it doesn't work in every single relationship, such as motherhood, right? If A is the mother of B and B is the mother of C, well then surely not A is the mother of C, surely not. So the question then we have to ask as we approach this new relation of parallel lines is parallelism transitive? Meaning that if A was parallel to C and B was also parallel to C, would A and B then be parallel to each other, assuming that all three lines, yes, are distinct? Well, if we assume that all three lines are distinct, then we'll have to actually then prove that this relation is true, because we can't just assume that transitivity will hold true. Let's take a look at the proof of this. So let's assume then, or we're given that lines A and C are parallel and line B and C are parallel. So in other words, we can mark these. A is parallel to C and B is also parallel to C. Is it then true that A and B will then follow as being parallel? Well, let's actually prove that this is true. Let's prove that transitivity parallelism is actually a thing. Here's how we're going to approach this. Let's assume otherwise. Let's assume that A is not parallel to B. What would that mean? That would mean that these two lines would have to intersect. So let's make these two lines intersect. Let's call that intersection point P. Now, you're thinking, okay, Mr. Gumler, there's already something wrong here because the lines are curving. But no, we are far past what the diagram looks like. So you cannot just say, oh, because the lines are straight, they wouldn't be able to intersect, right? No, we're saying that these lines will have to intersect. I don't care what the lines look like, right? We're not basing on what it looks like. We're basing on what is true. So A and B would then intersect at point P. Well, what immediately follows is a contradiction, because we're very close to the contradiction, because now we have two lines, A and B, that both pass through point P. Let's think about that. If A is parallel to C and B is also given as parallel to C, that means A and B are two parallel lines, I should say two distinct parallel lines to line C that both pass through point B. Why is then this a contradiction? Because of the Playfair postulate. We are allowed at most one line parallel to a given line through a given point. Thus, A and B cannot both pass through point P at the same time and also be parallel to C. That's a contradiction, which means our assumption is wrong. We assume that A and B were not parallel, which means we can toss that assumption out. What our conclusion then would be is that A is in fact parallel to B. And what that does conclude for us is it adds a new property of parallelism adds another property to parallelism, and that is the transitive property. Let's now take a look at a claim that Euclid made. This was actually something that he made in the beginning of his works, and he stuck to this claim, and this claim has caused quite a bit of controversy within the geometry system. Here's what his claim was. If a transversal forms a pair of consecutive interior angles that sum to less than 180 degrees, then the two lines cut by that transversal meet on the side of the transversal on which a consecutive interior angle pair sums to less than 180 degrees. So let's put his claim into an illustration. Below we have transversal T cutting through lines A and B. We're given such that angle 1 and angle 2 form a pair of consecutive interior angles. We're also going to be given that the sum of those two angles are less than 180 degrees. And you'll also note that they're on the right side of line T. What we're going to then prove is that A and B meet on the right side of T. Well, how are we going to then prove this? I'm going to leave most of this up to you for you to do on your own, but I'm going to give you a nudge. Let's assume the opposite. Let's negate A and B meeting on the right. Well, actually what happens then is if we negate that they don't meet on the right, there's really actually then two assumptions we have to then claim. If they don't meet on the right, then here's what we have to think. They either A and B don't meet at all, like they will never intersect. That's one of the possibilities if it doesn't meet on the right. And then the third possibility, or the second possibility in this assumption, would be that A and B meet on the left. So in order for us then to prove that A and B meet on the right, we're assuming that A and B do not meet on the right, and then we'd have to then show that these two possibilities, whether they don't meet or they meet on the left, will actually arrive at contradictions for both. So on your worksheet, you're going to take a look at Euclid's claim, and you're actually going to have to show that both of these possibilities will reach a contradiction, which then means you could toss them out, and there's only one possibility remaining, and that would be A and B do in fact meet on the right. Now, this is actually kind of a continuation of our thought here as we progress into some more kind of generic uses of what we know about our parallel lines. So in the diagram below, it says, consider the quadrilateral. I've labeled the four sides, A, B, C, and D. Are any of the sides of this quadrilateral parallel? Well, no, it's also given that angle 1 and angle 3 are measured as equal, and angle 2 and angle 4 are measured as equal. Well, what would it then take for these two lines to then, or these pairs of lines to be parallel? If I want to show that, let's say, D and B are parallel, what would then have to mean? So I'm going to kind of give you guys some advice on where you're going to go on your worksheet. What would this have to mean is that the measure of angle 1 plus the measure of angle 2, because those are consecutive interior angles, if those are consecutive interior angles, then if I want the lines B and D to be parallel, they would have to add up to 180 degrees because they'd have to be supplementary. And that means because we have a pair of consecutive interior angles that are supplementary, the lines would be parallel. But it's more of a question. Do we know that angle 1 and angle 2 would add to be 180 degrees? So let's actually then prove that angle 1 and angle 2 would have to add up to 180 degrees. How are we going to do that? Well, as you guessed it, we're going to assume the opposite. Let's assume the negation that angle 1 and angle 2 are not equal to 180 degrees. So what would then that mean? If angle 1 and angle 2 are not equal to 180 degrees, that means, again, we have two possibilities. We could have measure of angle 1 plus the measure of angle 2 is then less than 180 degrees, or we can have the measure of angle 1 plus the measure of angle 2 is greater than 180 degrees. So going with those two things, you're going to find contradiction of this. And here's your hint. Remember that if there is a sum of angle 1 and angle or a sum of consecutive interior angles that are less than 180 degrees, then by Euclid's claim, we know that they would intersect on that given side. So use that Euclid's claim then to help you answer the following question with these parallel segments. Now we turn our attention to just some more generic diagrams, where we're given a generic diagram, something given information about that, and we're going to prove some information about this. Now, I'm not going to necessarily structure the proof here in the slides, but I'm going to kind of walk through the idea of how we could reach conclusions. So we have parallel tests and parallel consequences in our possession, which means if we're given information about given information about our angles, right? If angles are such and such, then the lines are parallel, so we can prove lines to be parallel with our tests. Or if we're given lines parallel, then we can use those parallel lines to then reach conclusions about our angle relationships. So those would go, if lines are parallel, then angles are such and such. And those are the consequences that help us then prove angle relations. Well, if we take a look at this diagram here, we're given that the measure of angle 1 and the measure of angle 2 are equal to each other. We're also given that AB and CD are parallel, and that BC and DE are parallel. And you'll note that those are already marked in the diagram. Now, one thing you are allowed to assume is that lines that are angles that appear straight are straight, which is then important for us to know that this segment here, ACE, or the line that passes through them, all three of those points are collinear, because I see a straight angle there. And that's going to come in handy to actually prove that the measure of angle A and the measure of angle E are equal. Because let's have a look at what's happening. The line that cuts through points A, C, and E, as you see, because that is a straight angle, it forms a transversal. Note that it's cutting through this set of parallel lines and this set of parallel lines. And because it is a transversal cutting through a pair of parallel lines, we know then the angle relationships hold. So let's take a look at what then unfolds. Take a look at angle A. Notice anything in relation to angle 2? That's right, angle A and angle 2 are actually equal by the corresponding angles consequence, right? Because the corresponding angles, because they're corresponding angles, we know that they'd be equal because we're cutting through parallel lines. And take a look at angle 1 and angle E. What's their relationship? Oh, that's right, another bout of corresponding angles consequence. So that times 2, and we now have another equal pair of angles. So this is what we have so far. we're given that angle 1 is equal to the measure of angle 2. By the CAC, we were able to say that the measure of angle 2 is equal to the measure of angle A, and we also, again, by the CAC, determined that the measure of angle 1 is equal to the measure of angle E, which means by a very big happy family of transitivity, I can then prove that the measure of angle A is equal to the measure of angle E, and there we have it, QED. So you're going to structure your proofs, okay, when you jump into some generic problems on the homework assignment. So please don't just walk through it brisk, or don't walk through it without any detail. You're going to add the detail to your proof. That could be column form or paragraph form. I just don't have enough room in the slides to necessarily construct the entire proof. So I'm just walking through logically of what this would look like. Let's continue our thoughts then into some generic proof. Here we have a similar diagram, but I've changed some of the given information. In this case, we still have angle 1 and angle 2 equal. We're also given that angle A and angle E are equal. Notice that I use double hash marks. I don't know all four are equal this time. And I'm also still given A, B, and C, D are parallel, but this time I'm going to prove that B, C, and D, E are parallel. Well, in order to prove lines parallel, I'm going to have to use a test to actually prove lines parallel. Again, I'm allowed to assume that ACE is a straight angle, which means that's my transversal cutting across. Let's now take a look at some angle relationships. I know that angle 1 and angle 2 are equal. I know angle A and angle E are equal. But again, since A, B, and CD are parallel, I know something about the measure of angle A and the measure of angle 2. They're corresponding. So the measure of angle A is equal to the measure of angle 2 because of the corresponding angle's consequence again. What does that mean for us? That means I can prove by transitivity of equality that the measure of angle 1 is equal to the measure of angle E, right? Because if I'm given 2 is equal to 1 and, I'm given 1 is equal to 2, and now 2 is equal to A, and A is given to us as equal to E. That means 1 is equal to E by the transitivity of equality. What does then that lead us to? We'll take a look at what angle 1 and angle E form, right? Angle 1 and angle E are another pair of corresponding angles, which then means if they're an equal pair of corresponding angles, which they are, I can declare line BC parallel to line DE by, this time, it's the corresponding angles test. Because remember, the test says if you cut two lines with a transversal and you find that the corresponding angles formed are equal, then the lines are parallel. So by the CAT, that means I can prove those lines to actually be parallel to each other. Let's take a look at another example. We have this now. Well, I know we haven't talked about a trapezoid yet, but this would actually be defined as a trapezoid. But let's just call this a quadrilateral with precisely one pair of opposite sides. So we have AB is given to us as parallel to DE. We're also given that AM and BM are equal. We're going to prove that DM and CM are equal. And way we can do this is using our angle relationships. Let me point out a really cool thing that's happening. Since AB and DC are parallel, what's happening is that these diagonals, BD and AC, they're transversals, which means we form angle relationships. So let's take advantage of those angle relationships. In my given, I'm given that AM and BM are actually equal to each other, which means you notice what type of triangle AMB is. It's an isosceles triangle. So I can immediately claim that those two base angles there are equal. So I'll just go ahead and call those measure of angle MAB is equal to the measure of angle MBA, and I know that by ITT. Where am I going to go with this then? Well, I'm going to take a look at some other my angle relationships. In particular, take a look at angle MAB and angle MCD. Notice what their relationship is since those lines are parallel. Those are alternate interior angles, which means I can claim the measure of angle MAB is equal to the measure of angle MCD, and that is by the AIAC, because the lines are given as parallel, so that's by consequence I know the alternate interior angles are equal. I can do the exact same thing with the measure of angle MBA and the measure of angle MDC. It is also a pair of alternate interior angles. So then by transitivity of equality, I know that MCD is going to be equal to the measure of angle MDC, and that is by transitive equality. So what am I just then figured out? I just figured out that in this triangle MDC, that I have two equal angles. Hey, what can I say then about their opposite sides? I can say the opposite sides would also have to be equal, such that DM is equal to CM by the converse of ITT. Isn't that fun? In the same proof, we've got ITT and con ITT. Pretty fun. Now, this last proof, I'm just going to kind of talk about what you're seeing here, because you're going to see this actually on the worksheet. Let me explain what you're seeing here, all right? We have an isosceles triangle. So AB is equal to BC. Okay, that's what you're seeing. What else you're seeing is that D is a midpoint. So D is midpoint. Okay. What's happening is that our line ED, okay, that line ED, I should just do that. ED is parallel to one of the legs of our isosceles triangle. It's parallel to BC. At the same time, FD is also parallel to the other leg, AB. Okay, and what you're going to prove, and I'll just go ahead and highlight these. What you're going to prove is that this triangle here, ADE, and this triangle here, CDF, are congruent to each other. So prove that those two triangles are actually congruent using what we have in this information here. We do have parallel lines, we do have a midpoint, and we do have it being an isosceles triangle. So use that information then to arrive at the conclusion that those are actually congruent triangles. And you'll see that on the worksheet. All right, we come to the end of our lesson. If you do have any questions, please be sure to email me. With that, be good and do good.